Hey guys, welcome. Yeah, so our second video on groups, and so for a thorough introduction into what groups are in mathematics, you should watch that first video where I promised that in this second video I would show you how to add with fruits. So the answer to the question in the subtitle, wait, you can add with fruits, is yes, and this is exactly how. Okay, now let's define the set S that has the elements apple, banana, and orange, and let's say that our binary operation, which is symbolically represented as the same as the plus sign, is juicer. So juicer is how we combine two elements in the set. Yeah? Okay, cool. Now, this is how we can make one way. This is not the only way, but this is one way we can make this set together with juicer a well-defined group. And that is by showing this Holy table, which is a group table where we have a well-defined group with this set and the binary operation juicer. And this is how. Well, what are the requirements to make a group? For us to say that we have a well-defined group, what are the requirements? Well, we need a neutral element, so something that acts like 0 does with respect to the usual addition, right? Okay, well, that here is apple, because if you look at the two rectangles that are highlighted in red vertically here and horizontally here, then they show clearly that apple is the neutral element, because anything that combines with apple is that thing itself. So apple, when combined with another element in this set, does not change that element, and therefore apple is the identity element. All right, so one of the requirements fulfilled. What's another requirement? Well, we need an inverse element for every element. So an inverse is an element that pairs with a particular element to make the identity. Well, so here we can see that apple has apple as its inverse, because apple plus apple make apple, where again apple is the identity element or the neutral element. Okay, and then banana is its own inverse, because banana plus banana makes apple right here, right? And so banana is banana's inverse. And orange is orange's inverse, because orange plus orange makes apple, the identity element apple. Yeah? Okay, cool. Now, I've also highlighted that this group is not commutative. When a group is commutative, we say that the group is abelian. Yeah, and I show that it's not commutative because banana plus orange here in what's the blue circles, banana plus orange makes banana, whereas orange plus banana makes orange. So you see banana plus orange is banana, which is not the same as orange plus banana, which is orange. Yeah, okay, cool. Then next, well, we didn't have to fulfill commutative property because that's not a requirement of groups, just pointing out that this group is not commutative. But yeah, one requirement that we already fulfilled was the existence of a neutral or identity element. That's met. And then we also have fulfilled the existence of the inverse element. And so we only have two additional requirements. Closure, which is clearly visible from this Holy table. And closure just means that when two elements combine, what they make is also an element of the set. Yeah, and that's clearly true because, well, if you look at like this right hand side 3 by 3, that's the result of all the combinations in the set, and they're all in the set. Yeah, okay, that's an easy way to see that closure is fulfilled. So what's the final requirement of a group? Well, we need it to be associative. We don't require that it be commutative, but we need it to be associative. Okay, so then let's look at this skeletal map of the same group. So A is apple, B is banana, and O is orange. And this is identical to this other table. It's just less visually appealing, if you will. And yeah, so associative property would have us consider all the different ways of grouping A plus B plus O, right? And so since there are three distinct elements, A, B, O, there are a total of 6 permutations or rearrangements of those, right? And therefore we have to check the associative property in 6 different cases, and it's met every single time. And this is another promise I made in the introduction video, which is that in the second example, I will exhaustively show that the associative property is met, and clearly I have kept my word. All right, now you can check the associative property in each of the cases I've displayed carefully on your own time if you'd like, but we can look at one of them. And why don't we look at this very first one? So here we're checking if A plus B and then in turn plus O is the same as A plus B plus O done first, right? Okay, all right. Well, A plus B according to the table is, well, we have A here and then B here. So A plus B in that order would be B. And so I've got A plus B is replaced with B here. And so then plus O, right? And then on the right hand side, B plus O is, well, here is B and here is O. So B plus O is B. And so we have that the right hand side then is A plus B. And B plus O is, if you look in the table, it's B, and A plus B is also B, so we have B equals B, and so the associative property is met in this first case. And as I said, I've displayed them. Check them carefully yourself if you'd like, but otherwise, yeah, I hope you really enjoyed this. Keep watching. Take care. Fuck me. This was so annoying.